Potential in human cells. Some cell walls in the human body have a layer of negative charge on the inside surface and a layer of positive charge of equal magnitude on the outside surface. Suppose that the charge density on either surface is sigma equals plus or minus 0.5 10 to minus 3 coulombs per meter square. The cell wall is T is equal to 5 nanometers thick and the cell wall material is air. Part A, find the magnitude of the electric field in the wall between the two layers of charge. So we have this membrane cell wall. We have a positive charge on the outside surface, negative charge on the inside surface. Its thickness is T, and the electric field points from the positively charged surface to negatively charged surface. So here is our coordinate system. So the electric field points in minus j hat direction, as you can see in this figure. Now, for an infinite sheet of charge, we can find the electric field due to this sheet of charge using Gauss law. Here is a Gaussian cylinder. Because the electric field is going to be parallel to the area vector for the top surface and bottom surface and perpendicular to the area vector for the side surface, we can write Gauss law as the closed surface integral electric field dot product with area E dot dA is equal to the magnitude of the electric field. For the same distance from the two sides, the magnitude will be the same, and the electric field is parallel to the area vector. So we have 2A for the bottom and top surface. So EA from the top, EA from the bottom. This is equal to the charge enclosed by the surface Q inside divided by epsilon 0. How much is the charge enclosed? The charge enclosed is the charge in this area, which is the charge density sigma multiplied by this area A, which is also the top area or bottom surface area. So this is going to be equal to sigma times area A divided by epsilon 0, which tells us that the electric field magnitude should be equal to sigma divided by 2 epsilon 0. Now that's for a single positively charged sheet. We have both a positively charged sheet and a negatively charged sheet. The electric field due to each one of them is sigma over 2 epsilon 0, so they add up in between. So we can write the total electric field as E is equal to electric field due to the positively charged outside surface plus the electric field due to the negatively charged inside surface. They are both sigma over 2 epsilon 0 pointing in minus j hat direction minus sigma over 2 epsilon 0 j hat. So they add up to give me a total electric field minus sigma over epsilon 0 j hat. Now, what is the magnitude of this electric field? That was the question. The electric field magnitude is sigma divided by epsilon 0. This is basically our symbolic answer. And if we substitute the numbers here, first of all, we need to note here that epsilon 0 permittivity of free space is equal to 8.854 times 10 to minus 12 Coulomb square over Newton meter square. And remember that the surface charge density was given in the problem statement as 0.5 times 10 to minus 3. Let's check the units. It was coulombs per meter square, 0.5 10 to minus 3 coulombs per meter square, divided by epsilon 0, which is 8.854 times 10 to minus 12. So this gives us an electric field magnitude 5.6 times 10 to 7 volts per meter, the SI unit of the electric field. All right. Now let's move on to part B of the problem. Part B, find the potential difference between the inside and the outside of the cell, which is at the higher potential. So let's see the potential difference between the inside and outside. So I'm going to call the outside surface A, inside surface, surface B. The potential difference, delta V, is equal to potential of A minus potential of B. So this is basically VAB. This is minus the path integral from going from surface B to surface A, electric field dot product with displacement, and I'm going on the y-axis, E dot dy. So this is going to be minus the path integral B to A. Electric field has magnitude E pointing in minus j hat direction. The displacement going from B to A, I'm moving on the positive y in the positive y direction, so that's plus j hat. So this is dy in j hat direction. So that gives me E dy, the integral of dy, because I have a minus sign and minus sign here, these minus signs will become plus. J hat dot j hat is 1, so E dy gives me E times y when I evaluate the integral performed, evaluated between B and A. This is basically equal to E times the thickness of the cell wall, E times T. So that tells me that the potential of surface A with respect to the potential of surface B, which is VA minus BB, is equal to electric field magnitude E times T. So that was basically sigma over epsilon 0, sigma T divided by epsilon 0. So that is the potential difference. Now, if I plug in the numbers here, potential of A with respect to B is the electric field magnitude 5.6 times 10 to 7 volts per meter. The thickness was 5 nanometers, 5 times 10 to minus 9. So I find that the potential difference VAB is 0.28 volts. So VAB turned out to be positive. So here, let's make a comment about this. Since VAB is positive, remember that A was the outside surface. The outside surface, the positively charged surface, is at a higher potential. So this is basically our answer as to which one is at the higher potential. So that answers the potential difference between the inside and outside of the cell, and we also found which one is at the higher potential. Now let's move on to part C. A typical cell in the human body has a volume V of 10 to minus 16 meter cube. Estimate the total electric field energy stored in the wall of a cell of this size. And there is a hint, assume that the cell is spherical and calculate the volume of the cell wall. All right, so in part C, we have a spherical cell. We're assuming that the cell has a perfectly spherical shape, so that its volume, the volume of the cell, is equal to 4/3 pi radius capital R cube. And the volume of its wall is basically the surface area 4 pi capital R square multiplied by the thickness T. Now this tells me that I can write the radius R in terms of the volume V. So it is a volume of the cell is what we called V. So it is 3V divided by 4 pi to the power 1/3. So with that, the volume of the wall, cell wall, becomes 4 pi R squared T. So it's going to be 4 pi 3V over 4 pi to the power 2/3, because it's R squared, multiplied by T. And this is equal to, if I put this 4 pi inside this parentheses, it's going to be 4 pi so let's carry that as 4 pi to the power 3/2. Then I have 3V divided by 4 pi, all inside this parentheses, which is to the power 2/3, multiplied by thickness T. Now 4 pi to the power 3/2 divided by 4 pi is 4 pi square root. Let's see, it's going to be square root of 4 pi. So I will have square root of 4 pi times 3V to the power 2/3 multiplied by thickness T. So that's the volume of the wall. How much is the stored energy? The stored energy density, is given as 1/2 epsilon 0 magnitude of the electric field squared, and the total energy stored will be equal to the energy density multiplied by the volume of the wall. So if I substitute for this energy density 1/2 epsilon 0 E squared, remember E squared, E is sigma over epsilon 0, so it's going to be sigma squared divided by epsilon 0 squared. The volume of the wall is T inside the parentheses square root 4 pi 3V to the power 2/3. So epsilon zeros will cancel. We will leave only one epsilon 0 at the bottom. So we can write the total stored energy. Total stored energy, potential energy, will be capital U, which is sigma squared T divided by 2 epsilon 0, 3V square root of 4 pi to the power 2/3. This will be the total energy stored. Now we can evaluate this for the given numbers. U is equal to sigma is 0.5 10 to minus 3, 0.5 10 to minus 3 square. Thickness is 5 nanometers, 5 times 10 to minus 9 meters, divided by 2 epsilon 0, 2 times 8.854 times 10 to minus 12. And then we have 3V. How much was the volume? The volume of the cell is 10 to minus 16 meter cube, remember. So this is 3 times 10 to minus 16 square root 4 pi to the power 2/3. And the energy we calculate here, U is equal to 7.4 times 10 to minus 15 joules. Let's move on to part D of the problem. Part D. In reality, the cell wall is made up not of air but of tissue with a dielectric constant of 5.4. Repeat parts A and B in this case. Okay, now when we have a dielectric, the permittivity of free space epsilon 0 is going to be replaced with the dielectric constant kappa multiplied by epsilon 0. So that the electric field magnitude, instead of being sigma divided by epsilon 0, will become E prime is equal to sigma over kappa epsilon 0. This is the new electric field magnitude. So in terms of the previous answer, the electric field is actually reduced. E prime is going to be equal to the previous answer E divided by kappa. So if I substitute the numbers here, it was 5.6 times 10 to 7 volts per meter divided by kappa, which is 5.4. So that gives me the new electric field magnitude E prime to be 1.0 times 10 to 7 volts per meter. In part B, we calculated the potential difference delta V, and we found that it is the electric field magnitude E multiplied by the thickness of the cell wall. And here we have a new potential difference, delta V prime, which is E prime multiplied by the thickness, which is sigma T over kappa epsilon 0. This is our new potential difference. And if I substitute the numbers here, we have delta V prime is the previous potential difference I have calculated divided by kappa. So that is 0.28 volts divided by 5.4. So I find that the new potential difference, delta V prime, is 0.052 volts. All right. So in this problem, we've looked at a cell wall. The cell wall has a positively charged outside surface and negatively charged inside surface. There is a surface charge density sigma. The cell wall is 5 nanometers, thickness is T. First, we calculated the electric field in the cell wall. So that's the electric field that develops between a positively charged sheet and negatively charged sheet. And I recalled using Gauss law that the electric field due to an infinite sheet of charge, positive sheet of charge, is sigma over 2 epsilon 0 on two sides. If you put a negatively charged sheet here, it will also have an electric field sigma over 2 epsilon 0, and they will add up to give me sigma over epsilon 0. Sigma over 2 epsilon 0 multiplied by 2, and it's pointing in minus j hat direction. So when I substitute the numbers, I get the magnitude of the electric field. The potential difference between the outside and inside surface, VA minus VB, is the electric field multiplied by the thickness. So I called the outside surface A and inside surface B. Delta V, VAB, VA minus VB, is minus the path integral B to A, electric field dot product with displacement. So that gives me 0.28 volts. And since I find a positive value for the potential difference, outside surface appears to be at a higher potential. Then I have assumed that the cell is spherical in shape. It has a volume V, which is 4/3 pi r cube, and the volume of the wall is then 4 pi r squared t, the surface area of the sphere multiplied by the thickness of the wall. And r can be written in terms of v as 3v over 4 pi to the power 1/3, and then I can write the volume of the wall as 4 pi r squared t, substituting for r, the value, the expression I have here. So I get square root 4 pi 3v to the power 2 over 3 times t. The stored energy density is 1 over 2 epsilon 0 e squared. This is energy stored per volume. The total energy is the energy density, energy per volume multiplied with the volume. So that is 1/2 epsilon 0 e squared, sigma square over epsilon square, epsilon 0 square multiplied by the volume of the wall, which is 4 pi r square t. So that gives me the total stored energy, and when I substitute the numbers, I get my answer. If I have the space in between the two surfaces filled with a dielectric, not air, so epsilon 0 becomes kappa times epsilon 0. I see that the electric field is reduced to the original electric field divided by kappa, and because the potential difference is electric field multiplied by thickness, it's also reduced by a factor of kappa, the dielectric constant of the tissue.